Hello everyone, so today we're going to go over a problem from the practice problems of work, energy, and power. So whatever unit that is what you guys are doing, this is a problem that relates to power, and specifically is number 69 on the Cutnell book, just in case you guys want to, I don't know if you guys are using that book or not, but 69 from the Cutnell practice problems. The motor of a ski boat generates an average power of 7.50 times 10 to the fourth watts when the boat, because power is measured in watts, when the boat is moving at a constant speed of 12 meters per second. When the boat is pulling a skier at the same speed, the engine must generate an average power of 8.30 times 10 to the fourth watts. What is the tension in the tow rope that is pulling the skier? What we have to do first in every physics problem, I'm pretty sure Ms. Elizabeth has probably told you this, list down all your variables. And like if you can draw a diagram, then draw a diagram. But so as we know, the first variable, like this is how I thought about for this problem, the first variable that's kind of given to us is the motor for ski boat generates an average power of when the boat is moving at a constant speed of 12 meters per second. So when a boat is moving, so we can just picture it like this. The most awesome boat you've ever seen. Gorgeous. When the boat is moving at a constant speed of 12 meters per second, its power, just say its power equals 7.50 times 10 to the fourth watts. So from what we know, this is when the boat, it doesn't say anything about a boat pulling a skier. So this boat, so our first power variable, so like we can separate them in like between like what's our initial power and what's our final power based on what they're giving us from the problem. So since they're asking us what is the tension in the tow rope that is pulling the skier, we know that that's the final power that the boat's gonna have. So to kind of list it down in a way that it's more like visually pleasing and understandable. So our power initial in this case is the boat itself without pulling the skier. It's just the boat itself when it's going at 12 meters per second. We know that its power initial is going to be 7.50 times 10 to the fourth watts. So but now when and we know that, well, in this case the velocity initial, well, the boat itself without pulling the skier is going at a constant speed of 12 meters per second. So we can just do 12 meters per second like that. When the boat is pulling a skier at the same speed, so now they're introducing the same boat, but now it is pulling a skier. So this is in this case. If you're gonna look at that, this can be like a case like here, and now it's the same gorgeous looking boat. It's just they're still going at 12 meters per second. So I realized that I didn't really give much of an explanation as to why the speed of that boat was 12 meters per second, but in the problem itself says the boat traveling at the same speed. Therefore, we can assume that the initial speed is also the same as the final speed. So now the boat itself has a new friend. Well, in this case is the rope. It has a new friend that is pulling on the skier. We're guessing is the water skier. He or she is having so much fun. They're just really just having fun in the water, just having the most fun they can have. And what is the tension? Label your variables always. What is the tension in the tow rope that is pulling the skier? So we can assume that this is what they're asking for. They're asking for the tension in this tow rope. This is the tow rope. This is the tension that they're asking us about. Now, we can list our variables for this situation, as since now like this kind of like the after. Think about it like the final power, in a way, because it's like the power that is given in the situation that is being asked about the variables. So I don't know if that was a good explanation, but an average power of, so this is the power of the boat when it's pulling the person. We can assume that this is power final equals 8.30 times 10 to the fourth watts. And then well, it's velocity final, we can just assume that it's just 12 meters per second. But they're asking us for the tension. So the tension we don't really know, and that could be your x, your t, your y, whatever you want it to be. And I'm pretty sure the way Mr. Lazarbe wants it is t as your tension. Now, what we do know is that tension is a force. So we know that, and this is like the only force that is technically being acted upon in this system, is this tension. So we can assume that tension equals force. Now, there is a set of power formulas that these power problems, and they're very simple, but they can go a long way. You can extend them, but minimize them. We know that power is work over time. That's it's how it is. But which in this case it can just be labeled as W/T. Power is also the change in energy over time, which can be labeled in like that. Change in energy over time. Sorry, my handwriting is awesome. It's magnificent. And then we know that power, actually the change in power, to be specific, change in power equals force times velocity. We do know that velocity is a vector. So, but power itself is a scalar. So what we can do now realize things is we can see from these three equations which one would definitely work in our problem. So as we can see, out of all these, this one is the one that seems to be like it has the variable that we want. Since we already established that force is tension, because tension is a force. Now, so we know, so as we, oh, look how convenient, change. Okay, so as we know, the change in, I don't know, energy, power, work, we know that is basically, that's basically just saying your final power, work, energy, distance, whatever it is, minus your initial power, work, initial velocity, whatever it is that you're trying to find. You know, the change is just the final minus the initial. Now, we already established before what our final and our initial powers were, as we can see here, and we already know what the velocities are, which is the constant. Since it's a constant speed, we can assume that the speed is the magnitude of velocity, because remember that velocity is a vector and it has a direction and magnitude. So if we look at this, it says the constant speed. So we know that the velocity of the boat, we can just assume that it's 12. So in our formula, they're not asking us for the change in power. They're not asking us for the velocity. They're asking us for the tension. We can then move. And we know that tension is force. Tension or force. So this changes into tension. So this is change in power equals tension times velocity. Now we do know that if we can just move this around in order to have it more comfortable, like find the variable that you really want. So we want tension in this case, so we move tension over to the left, and we move change in power over to the right over velocity. Now, since we had already established what our final velocity were, because this velocity, this is the power that they're asking us, that they're giving us when it's pulling a skier, and then they're asking us for the tension when they're pulling a skier, but then they also give us what the initial power was before pulling a skier. So we can think about this before and after the skier. So like before or during the skier. So we know, as a more simpler way, so we know that our power final, because we know that change in power is just change power final minus power initial over velocity. So we know our velocity 8.30 meters per second. We know our final power is measured in watts. So we know that our
Then
power
get a problem
initial
wrong.
is, so our power before the skier, so our initial power, 50 times 10 to the fourth watts. Now, we have all of our variables here. The only thing we have to do for what we have, plug in order to find what we need. So we know that tension in this case equals 8.30. I like to kind of keep stuff in parentheses when I'm plugging in, just to show that I'm substituting values in. Times 10 to the fourth watts. You don't really have, I don't know how Miss Lozarbe wants you to do it, but I usually don't really put variables when I'm plugging in. I'm just doing it in case so you guys can follow along. The units, I can just leave the units until the end, but it's also helpful to sometimes have them just in case you, for some reason, you are able to cross them out and find exactly what you need. So we know that our initial power is 7.50 times 10 to the fourth watts over 12 meters per second. Now, don't fret. If you have to do this, I'm pretty sure you can just use your calculator, whatever it is. Just if you do know how to subtract and stuff from scientific notation, that's great. You can still use your calculator. Or if you don't, then learn how to do scientific notation subtraction. But I think you're really gonna need that. So we know that the units for force are Newton, and we know that tension equals force. Therefore, you can use that to show therefore. Therefore, we know that the units for tension also have to be newtons. So we know that whatever we get, whatever number, astronomical number we get, or a little number that we get, we know that the units for tension, they have to be whatever number, newtons. And that can save you a point, 2 points, I don't know, however it is. That can save you a lot of points, and it can give you a partial credit or whatever it is. We know that these are the units. So you should really know. It's good to know your units by memory, but like you don't really have to. You can just find like what watts is and all that stuff. But if you do plug everything into your calculator or subtract it and divide, and you're a genius, you should get 6.7 times 10 to the second, pretty sure, to the second newtons. And this, my friends,